now the bring your own chair part is over. The bring your own beer part is still there. Okay. So last time I introduced the notion of countably infinite sets. That is, sets which are equivalent to the set of natural numbers. They are all called countably infinite sets, and we call their cardinality, and we denote their cardinality. Then, of course, the natural question that we ask are there uncountably infinite sets? For this, the answer was obviously yes, because this power set of n, the power set of any set has cardinality bigger than the original set, and therefore the power set of n must have bigger cardinality than this. Therefore, we must have uncountably infinite sets. Okay. Since the question is, are there uncountably infinite sets? The answer is yes. Why? Since the power set of PA, of any A, is of higher cardinality. We have proved this. We have proved this because A is obviously equivalent to a subset of PA, but PA can never be equivalent to a subset of A because there is no alternation. So this is higher cardinality. In particular, the cardinality of the power set of n is greater than the cardinality of n. This is one example of an uncountably infinite set. The set of all subsets of the natural numbers is one example. Okay, so therefore the set of all subsets of n is an uncountably infinite set. Okay, so now we are going to look at some more examples of uncountably infinite sets. Some more uncountably infinite sets. Okay, the first example is that the real numbers is uncountable. We'll assume that we all know what the real numbers are. So, though later I will discuss a more formal construction of the real numbers. So, the set R is uncountably infinite. The way we show it is again by contradiction. This is one of the finest pieces of proofs, types of proofs that mathematics was created. And Euclid had its proof that there are an infinite number of prime numbers by a simple proof by contradiction. And Hardy rates is one of the finest proofs he has ever seen. I think Erdős also rates it as one of the best proofs he has ever seen, one of the most beautiful proofs he has ever seen. Okay, the proof is, I'll go through these proofs in the beginning a little bit in detail because I think to get used to the notion of proving equivalence of sets. It will be useful later. Okay, suppose none. That is, suppose R is uncountably infinite. This implies R is countably infinite. R is infinite. No, it is not uncountably infinite. It has to be countably if it is countably infinite, it must be equivalent to n, and therefore the elements of R we must be able to write it as a sequence. Okay, this implies all real numbers can be written as a sequence. This is a simple proof. There is a certain amount of diagonalization idea involved in it, which will carry us through in many proofs that time. Okay, written as a sequence of F1, F2, F3, etc. What this means is there exists a function from n to r, which is 1, 1 and all 2. So F1 will be one real number, F of 2 will be another real number, F of 3 will be another real number. Since that has to be an onto function, it will exhaust all the real numbers. So all the real numbers can be exhausted by writing them in the order of in a sequential order, using the words order in a loose sense. Okay. This means, I'm just laboring on this point. This means that any x in R, if we take any real number x, must be equal to Fj for some j in it. Because all real numbers are listed here. So if you take a real number, it must go and fall somewhere there. So x must be equal to Fj for some j. We will show that this leads to a contradiction. Now, each real number has a decimal expansion. Each real number has a decimal expansion. Unfortunately, some numbers have two different decimal expansions. For example, half can be written as 0.5000 or 0.4999999 repeated. You follow some convention saying that only one of them we will choose. Okay. So for example, we will follow the convention that we will not choose infinite cycling of 9. So each real number can be written in a decimal expansion x is equal to some capital X, point x1, x2, x3, etc. where we follow the convention that an infinite cycle is recurring tail of 9 is disallowed. You can take this and throw the other one or this. Okay. Therefore, then it will be written in a unique manner. Then it becomes unique. Otherwise, there will be two possible representations for the same given. This throw away one of them just to make the unique representation. Okay. If that is so, F1 will have a decimal representation, F2 will have a decimal representation, F3 will have a decimal representation. So in general, let Fj be equal to x j dot x1, x2, x3. I put the capital X for the thing that is more the integral part of it, and the remaining is the decimal part. Okay. This is we can do this for every j. Therefore, this also will depend on j. So I will write it as x1j, x2j, x3j, x4j, etc. etc. Right. Now, Cantor showed that there is an easy way to construct an x which is not any one of these values. So you consider the real number x whose decimal expansion is x is equal to point x1, x2, x3, 0 point. x4, etc. Where I'm going to say what? Well, incidentally, where are all these xij's from? They are all in 0 to 9. It's a decimal expansion. Could have taken any other expansion, it's the same. Where I'm going to specify how I'm going to choose this x. Now I want to construct an x which is not in this list. So I want to construct the x such that it is not f1, it is not f2, it is not f3, it is not f4, and so on and so forth. So therefore, to make it not equal to f1, I will make the first decimal place different from the first decimal place of x1. The second decimal place different from the second decimal place of f2, and so on and so forth. So where xj is equal to say some 6 if xjj is not equal to 6 and equal to 5 if xjj is equal to 6. You could have chosen some 3 and 5 or 4 and 7, anything you want. What you want is wherever there was something, I put something else, and this is there, I put the other. Then see, obviously therefore, x differs from every one of the fj's. It will differ from f1 in the first place, because when x11 is equal to 6, x1 is 5. When x1 is not equal to 6, x1 is equal to 6. So the first decimal place will differ from the first decimal place of f1. The second decimal place will again differ from the second decimal place of f2 and so on. So therefore, x is not equal to fj for any j. Contradiction. Because all the x's are supposed to have been listed, and I found an x which is not listed. So if you assume that it is countable, then it can be listed and arrive at the contradiction that you are not listed, because I have found a number which is not listed. Therefore R is uncountable. It cannot be countable infinite, and therefore it is uncountable. The towel has vanished. Hence,
decimal expansion is what you are assuming.
huh?
Decimal expansion is the only thing you are assuming about.
Talk a little loud.
Decimal expansion is what you are only assuming about the real number.
Yeah, nothing more. And to get the uniqueness representation, I take one of them. You could take the ones with the recurring lines, or whichever ones you want to take. But you must make sure that you choose only one of them. Well, of course, this all presupposes that we know about real numbers. But we all know, at least we all think we know real numbers. Right. This part?
Yes, sir.
Okay. What actually I am doing here is the following. Let us write F1. F1 is x1 point, x1 1, x2 1, x3 1, x4 1, etc. Right? Similarly, F2 will have a representation x2 point, x1 2, x2 2, x3 2, x4 2, etc. and so on and so forth. Now what I am going to do is I am going to look at a number x which is equal to 0 point. I have to put a place. I go and look at this first number. If I want to build the first decimal, I look at the first decimal of the first number. And if it is, what did I say, 6. If it is equal to 6, I put 5. If it is not equal to 6, I put 6. So okay. So therefore, whatever it is going to be something x1 not equal to x1. Therefore, this number cannot be equal to this number. The next digit, I go and look at the next diagonal. If that is 6, I put 5. If that is 5, I put 6. Okay? This is not equal to x2. So therefore, it cannot be equal to this number. Now do this for all decimals. You got a number which differs from all the numbers. And therefore, this cannot be the listing of all. But we said this is the listing of all the numbers. And I stick on it.
How do we show that this doesn't work for rationals?
Pardon me?
How do we show that this argument won't hold for rational numbers? We said in the other class that they are countable infinite.
Yes.
So how does this argument doesn't hold for rational numbers? Q.
Why it doesn't hold?
No. If this argument holds for rational numbers, then you would have proved that even rational numbers.
Why it doesn't hold for rational numbers? Think about it. Okay. Why it doesn't hold for? That means you must know about decimal expansions of rational numbers. What distinguishes the decimal expansion of rational numbers? Okay, right, I'll leave it at that. Exercise, that's a good question. Exercise, try to find the answer. You must analyze what do we mean by decimal expansion for rational numbers, etc. I will leave it at this. Okay, because my actually I am not. This itself is too much. I wanted to do only one lecture on set theory and get to real numbers, but I am going more than what is necessary. Oh, anyway, when we come back to the real numbers, perhaps we will come back to this question again. Then my aim is to get, it's a good question, but we will not leave it at that. When I do real numbers, I will come back to it again, answer it. Maybe you will see the answer. Alright. Well, anyway, last time we proved that the rational numbers are countable. What are we doing next? Next I am going to show that however small portion, that is, when you take the entire real line, it looks like a very big set. So let me look at a small set, which is this opposite 0, 1. Okay. I equal to 0, 1. That is the set of all real numbers. That 0 less than x or less than open. Okay. Now I will show that this is no big deal. This is also as big as the real numbers. What should we do to show that this is equivalent to the real numbers? We have to establish a one-to-one correspondence. Now let me just suppose I take x and map it to x minus half. I think. What does that do to 0, 1? It maps it to minus half. Okay. And then I introduce a map here, multiplication by pi. So what will that take this to? Minus pi by 2 to pi by 2. Okay. So therefore, the map pi times x minus half takes 0, 1 to minus pi by 2 to pi by 2. Now we introduce another map, the tan inverse map. What does that map? Tan inverse by x minus. Now what happens to tan inverse when you go from minus pi by 2 to plus pi by 2? It goes to minus infinity. And at all stages, what is maintained? One-to-one and onto-ness is maintained. Therefore, the map, the function f mapping I to R defined as fx is equal to tan inverse pi x minus half is a 1-1 onto map. See, this is assuming that we know about tan inverse, etc. etc. Okay? Lots of things that are assumed. 1-1 onto map from I to R, therefore I is equal. Therefore, any open interval, any non-trivial open interval is equivalent to R, as big as this. You can take a very small open interval of length 10 to the power of minus 18, but still that is as big as the real numbers as far as the cardinality is concerned. The next observation that I want to make is the following. If you now take any not trivial open interval, okay, once again your linear map will take you from 0, 1 to AB easily. That we all of you know. Draw a picture it will realize it. So what do I have to do? Here is 0, 1. I have to draw a graph which starts at A when it is 0 and ends at B when it is 1. And we know given 2 points you can always find a straight line passing through the point. Find the equation with the straight line. It turns out that if you take the map x to A plus B minus A x, then what happens? When x is equal to 0 it is A, when x is equal to 1 it is B.
Sir, is that tan inverse or tan?
What do you mean?
Tan inverse or tan?
Oh, here? Okay.
It should be tan.
It should be tan. Okay, right. It's very hot, we get tan. I was thinking of the other way around. Going from there here, but suddenly I got this way, so that's what the tan. You're right. Okay. Thank you. Okay, therefore, this is a function. So fx equal to a plus b minus a into x is a 1, 1 onto map from I j. Therefore, j is equal to I. So both are equivalent now. But I is equivalent to R. We saw previously. Therefore, it says any open interval, any open interval, 0, A, B, is equal to. I have to assume that A not equal to B, otherwise it will be empty set. Any non-trivial open interval is equal to R. I'll make one more comment here. Suppose, so we have seen now several, this was 2, then therefore now 3, therefore any open interval is uncountably is equal to R. So now is another example. These are all essentially the same examples seen in different perspectives. Now suppose I take x to be any subset of R. Suppose you take any subset of R such that
Is there any specific purpose because of which you are using the different equation?
no, that's what I'm going to show. I'll come to that. Just you see, you always have one base. It's like when you are putting swara, you come back to a base level and keep going back and forth. So you have a reference point. You take open interval or closed interval, whatever you want. But it is always better, nice to start with an open interval. It's easier. Okay. Because of the minus infinity, open set. So these two easily you can push. Otherwise you may have a problem at least. Minus infinity and plus infinity. So but we are going to show that is of no relevance at all. Suppose x is contained in R such that x contains an open interval. Suppose x is contained in R such that x contains an open interval. So now therefore I am studying closed intervals also. Closed interval will contain a. So if x is contained in R such that, then obviously x is equivalent to R. You should be very careful when somebody says obviously. Okay, obviously x is key. Why? Why is it obvious? Well, clearly x is equivalent to a subset of which subset? Itself, namely itself. Now R is equivalent to a subset of which subset? That interval it can. So let's call it an open interval, namely J. Schroeder-Bernstein theorem. If A equivalent to a subset of B and B is equivalent to a subset of A, the two are equal. Therefore, by Schroeder-Bernstein, x is equal. So therefore, you can see now closed intervals are also equivalent to R, half closed, half open. Anything is already taken care of. You can even have an interval piece and some discrete piece if you want, and still it is equivalent to R. As long as it has this one open interval piece, then it is equivalent to R. Size wise, and topologically not. Okay, so therefore, it looks like you have this is essentially like too much new. Right. Any questions so far? Let me give you another example before maybe this one I will just skip very quickly. Suppose you now consider this rectangle in the plane 0 or 1 here. So I am going to consider this set, the set of all xy in R2. Something okay, 0 less than x less than 1. So we consider this rectangle. Basically, I have taken what is it, rectangle or square? A square is also a rectangle. Safer to say rectangle. Now, all I have done is for some, I don't know why, for some reason I am throwing this out. Okay, it's this one. Right, could have worked with that, doesn't it? Now, what I am going to do is clearly, these words obviously, clearly are dangerous, which is really clear. Okay. I will call this interval 0, 1 as I. Clearly, I is equivalent to a subset of x. Which subset? I itself, but I have to write it as a part of R2. So I can write I as the set of all xy in R2 such that 0 less than equal to x less than 1 and y is equal to. Write like this, then I see that it is a part like this. Okay. Because here anything is allowed as long as y is between 0 and 1. I have taken y to be 0, so that's all. Okay. Now if I show that x is equivalent to a subset of I, then I am finished that this whole rectangle or the whole square will be equivalent to this, and this is equivalent to R. So this will have as many elements as R itself. Okay, even if you go to 2 dimension, you are not getting too many things. That's what the idea is. Okay, so again the idea is simple. Once again, you can use decimal expansions, this is what our conventions I had before. Suppose next we show that x is equivalent to a subset of. Now, what is good by showing that x is equivalent to a subset of I? All I have to do is, if I get a function from x to I, which is 1, 1, I am finished. Because then you can take the range to be that subset, so it is 1, 1 and on to the range. So therefore, enough to show that there exists a 1, 1 function from, and the idea is simple again. If you take any point x, y in x, I want to somehow convert it to a number between 0 and 1. So I am taking a point in this rectangle with x coordinate and y coordinates. I want to go from there to the I, namely this interval. So what I do is, I write the decimal expansion of x. Again the convention that we had before, and you write the decimal expansion of y. Now you construct a number alpha, which is a number between 0 and 1. So it will also have a decimal expansion. So I am going to construct it by using these two decimals alternately. The odd places are got by the x and the even places are got by y. So therefore, this will obviously be a number between 0 and 1. So therefore we have xy to alpha, and it's 1 1. Why? Because if fx equal to fxy is equal to fx prime y prime blah blah, then x1 will be x1 prime, y1 will be equal to y1 prime, x2 will be equal to x2 prime, y2 will be equal to y2 prime. That means x will be equal to x prime, y will be equal to y prime, and so on and so forth. So that's a trivial writing up. So I will do that. These are 1 1 from x to y. So we have a 1 1 map and we are done, and therefore x is equivalent to a subset I. So we already had I is equivalent to a subset of x. Once again Schroeder-Bernstein, so the x is equivalent. Therefore, and which is in turn equal to, so therefore that's again an uncountable infinite set, and which is the same cardinality as the real numbers. Okay, well now that I have written all these things, I can as well write this. Suppose I have a set A1 which is equivalent to B1 and a set A2 which is equivalent to B2. Then I look at the Cartesian product and ask the question, well, the Cartesian product, sorry, if A1 is equivalent to A2 and B1 is equivalent to B2, is A1 cross A2 equivalent to B1 cross B2?
I think so.
The answer is yes. What should you do? In order to show that A1 cross A2 is equivalent to B1 cross B2, either you have to apply Schroeder-Bernstein's theorem with A1 cross A2 on one side and B1 cross B2 on the other side, or if you are lucky and clever or simple, the problem is simple enough, consider directly a 1 1 onto function from this to that. So I just write the 1 1 onto function. So A1 is equivalent to A2, B1, therefore there exists a mapping A1 to B1 which is 1 1 onto. This is a given thing because A1 is equivalent to B1. Again A2 is equivalent to B2 given, therefore there exists a G from A2 to B2 which is 1 1 onto. What is our aim? Our aim is to construct a 1 1 onto map from A1 cross A2 to B1 cross B2. So let me call A1 cross A2 as A and B1 cross B2 as B. Now obviously we will have to use the information that A1 is equivalent to A2, B1 is equal, A2 is equivalent to B2, which means we have to use this information, these functions f and g. So define f mapping A to B as follows. If you take any element of A, it must associate an element of B. So if A belongs to A means A is of the form A1, A2 because A1 cross A2 where A1 belongs to A1 and A2 belongs to. Since A1 belongs to A1, f of A1 makes sense. Since A2 belongs to A2, g of A2 makes sense. So f of A is defined as f of A1 g of, which is, this is in A1, this is in B1, this is in B2, so we can call it, this belongs to B1 cross. Because f takes A1 to B1, this will be in B1, g takes A2 to B2, therefore this will be in B2, therefore this is in B1 cross. Now, easy to verify. That f is 1, 1. Using the fact, that's it, it's very easy, trivial fact. Using the fact that f and g are 1, 1. So just suppose fa equal to fb, fa equal to fa prime. What does that mean? fa1 ga2 is equal to fa1 prime ga2 prime. Then the two coordinates must be equal. So fa1 must be equal to fa1 prime. But f is 1, 1. Therefore a1 equal to a1 prime. Similarly a2 equal to a2 prime. Therefore a1, a2 will be the same as a1 prime, a2 prime. That is 1, 1. And similarly you get the 1. So actually the combined force of this being 1, 1 and 2, this being 1, 1 and 2 makes this what fell down?
Nothing.
1, 1 and 2. So the combined force was very heavy. Alright. So one last remark to the following. No, not last. As a remark perhaps. Other things I say they are not remarks. Now, you take any interval I, open it, any interval I. You already seen that any interval I is equivalent to R. Therefore, for any two intervals, I and J. Because we saw that any interval is equivalent to R, first we saw open interval, then we show that anything that contains an open interval is equivalent to R. Then if I apply this result, it will tell me therefore I cross J is R cross R. That is, any rectangle in the plane will be equivalent to the whole plane. Just like we show on the real line that any interval is equivalent to the whole thing, we are going to show that any rectangle is equivalent to the whole plane. But then this, so therefore any rectangle is equivalent to R. But somewhere along the line, in this picture, we saw one particular rectangle which was equivalent to R. Okay. So we saw one rectangle equivalent to R. So therefore R2 must be equivalent to therefore the plane is no bigger in terms of its infinite size as the number of elements or whatever, the cardinality, than the real line itself. And now we can extend this argument. R3 will also have the same strength as R, R4, R5, Rk for any finite k will have the same strength. So similarly, for any k belonging to n or k is equal to if you take a cube like this instead of a rectangle, how do I establish the equivalence to this? I'll get an x1, x2, x3, y1, y2, y3 and the z1, z2, z3. Put x1, y1, z1, x2, y2, z2, x3. Then I'll do this for finite number. That's what this result is. Now one more observation in the following. The set of all subsets of n, the natural numbers, the power set, was one uncountably infinite set linear. Now R is another uncountably infinite set linear. It turns out both are of the same size. Okay. Now it's enough. If we show that Pn is equal to 0, isn't it? Why? Because 0, 1 is equivalent to R. Now that's very easy. So what do? I establish from here to here and so on. Maps. Suppose A belongs to Pn. I will associate a number here. So how do I associate a number? So then construct XA. Now it's a binary expansion. By its binary expansion as follows: point x1, x2, x3, etc. by its membership, where xj is equal to 1 if j belongs to A, 0 if j does not. What I am doing here is that particular decimal will get the one value if that particular index is in this subset A. If that index, suppose A is equal to 578, then the number x I will construct will have the fifth binary digit as for 1, 7th as 1, 8th as 1 and all the rest as 0. So that this we can construct this, then clear then A to XA is a 1-1 map from Pn to 0. So therefore Pn is equivalent to a subset of 0. Whenever you have 1-1 map, that means you take the range and it will be equivalent to that range. Okay, so with respect, starting with every subset, you construct a real number there in 0, 1. Now go the reverse way. Other map is start with x in 0, 1, its binary representation. Once again there will be two binary representation for some numbers, follow the convention, etc., etc. These are all now this thing understood. Then let Ax be the set of all those numbers j for which xj is equal to 1. Okay, so suppose your number is as the binary representation, etc., all other zeros, then Ax will be just 1 and 3. That's all. This is a subset of n. So this is a subset of n. belongs to P. Now therefore I have now a function from which takes the numbers to a subset. Okay. X to P, X to AX is one more. X to AX is a 1 1 from Pn from 0 1 to a subset of either 1 1 from 0 1 Pn. Therefore 0 1 is equivalent to a subset of P. Now use this and Schroeder-Bernstein theorem. This is equivalent to a subset of that is equivalent to a subset of this, and therefore by Schroeder-Bernstein, by star, double star and SB, we get Pn is equivalent to 0 1, which is equivalent. But we denoted the cardinality of this by 2 to the left naught, and this is equivalent to the cardinality of R, is usually written as C.
Sir,
Yeah.
so the one-oneness of this match A to XA.
Yeah.
Suppose we consider say 0.1
Yes.
and 0.0111111.
Yes.
They represent the same number.
Point.
0.1.
I told you. Convention you have to.
And ones are
You have to take only. The beginning itself we said whenever you have
they are
two
coming from two different sets from here.
I said that when you have to take only one decimal expansion. I don't understand your question.
Okay. Suppose your subset. I have two subsets now.
Okay.
The first subset consists of the number 1.
Yes.
The other subset consists of 2 and
The first subset consists of the number 1.
the next subset consists
2,
of
3,
2,
etc.
3, etc.
So your problem is that. This will go to what?
0.1.
Yes.
This will go to 0.0111, which actually don't exist.
Because of the fact what? Why?
No, they represent the same real number 01, right?
Yes, that's right.
So the function itself is not defined in some sense.
Now let me from where to where you are going? From the subset to.
Yeah, from the subset
You are
to
right.
0.
You are right. So let me see where is the technical mess I made. It is this place, right? Where was I? A to
A to X.
A to XA. Good question. You got me there. So let me think about it.
Sir, how about embedding zeros in between each and every bit?
Sir, when we take set of natural numbers, as such we haven't assumed infinity. So what is 2, 3, 4, 5, 6, we cannot just leave it as such. So we have to say some number.
No.
Here is the genuine
Just one
point.
complement.
Here is the genuine point. Okay, that's for granted. This is a subset of Pn, and this is also a subset of Pn, and he is claiming that these two represent. Okay. Okay, I will get back to you. This side technical point there. We'll have to start it off. Okay, let's say with that question mark, which I will sort out, Pn is equivalent to R. Well, yeah. Somebody has an answer? Yeah, quickly.
An alternative rule actually. Let a point in PA be n1, n2, n3, etc., where they are taken in ascending order. Then the corresponding real number is point n1, n2, n3.
Is that it?
So let the set, let an element x belong to Pn be n1, n2 means the set n1, n2, n3, etc.
Take the decimal expansion with
Take point n1, n2, n3 as the function.
No, what do you mean by decimal expansion then?
10, 11.
Oh, 10, 11,
Point
yeah.
N1, N2, N3, all the integers.
No, 10,
All
10, 11.
So you think of it as no, no, I think that will create more problems. Okay? Much more. Okay, I agree. I mean, if you don't see it quickly, let's me not confuse you with more and more discussion. I will start it out. Okay. But let me just want to. My aim was to conclude with a few comments. Okay. That's a good question. I might never thought of that. That's why you should keep teaching the same thing again and again. Every time something new. Good. Okay. Now, I just want to make a few comments and then get to making some remarks about these cardinal numbers. Okay. The first thing is, we have these natural numbers and we have these uncountable sets. Okay? We have this 1, 2, 3, etc. First we have the thing, then we have the big sized natural number, then we have all the uncountable sets. Now, we have already seen that any infinite set has a countably infinite subset. So you can't get anything smaller than countably infinite as far as infinity is concerned. Because every infinite set must have a countably infinite subset. So that's the lowest level that you get. It is like the rest of it is only something going on appending to the countably infinite sets. Okay. So therefore this Aleph naught is in a sense the smallest level of infinity that we can think of. The next level, one way is the Pn. We have the Pn here, which is 2 to the Aleph naught, and we saw that this is the same as the set of all real numbers. Now the question that Cantor raised, somewhere around 1870 plus, okay, was, is there any set in between? Is there any infinity in between? So is there, let me write that question, is there any infinity between Aleph naught and C? Okay, now let me put this question again reword this question. What does this mean? It must be bigger than Aleph naught. So that means first we want it was bigger than Aleph naught. Next we want it should be less than C. Now what does this mean bigger than Aleph naught? So we want a set A. Question whether we can get such a set A such that N is equivalent to a subset of A, because then only it will be bigger than Aleph naught. But A is not equivalent to a subset of, because if this is also equivalent, then the cardinality of A will be equal to Aleph naught. I want to go bigger than Aleph naught. So I want a set A in such a way that N is equivalent to a subset of A, but A is not equivalent to a subset of N. Next, what do I want? It should be less than C. That means A must be equal, so and A must be equivalent to a subset of R, I want to call it, but R is not equivalent to any subset of, that would make it smaller than C. The question is, can we construct such a set? Now Cantor believed no. That was around this. He believed that the answer is no to this. And that is what is no. In other words, the next level of infinity after Aleph naught must be the real numbers level. And that is what is known as the continuum hypothesis. I will just write this. I am not sure about the spelling, double U's or one U or what. So from now on, I call it the CH, the continuum hypothesis. Now, Not only Cantor, but a lot of fellows spend their time trying to, well, incidentally, still, we should say that at the time of Cantor, the formal axiomatic set formulation of set theory was not complete. Still a lot of ideas were being floated, but the idea was whether from the other ideas of loose axioms of set theory whether this could be proved. Okay, let me just give you two or three statements connected with this. Somewhere along 1900 plus, well, incidentally, Hilbert, in his famous address in the 1900, in the second Congress of the International Congress of Mathematics, listed a lot of unsolved problems, 23 of them I think. This was the first one he discussed, the continuum hypothesis. He considered that as a very important problem from the foundation's point of view, and his surmise was that it should attract the attention in the 20th century, and it did. Okay. But set theory was, in a sense, axiomatized. I'm going to put it these things in a loose way. Basically, there were this by the two between 1900 to 1920. This formalization of set theory was, in a sense, put in proper order. What it means is it was something like trying to put these things along the lines what Euclid did for geometry. Here are a set of axioms, now all these theorems. Okay. Now when these two fellows put this, then the question was, is this a theorem? The question was, so we will call this, is usually referred to as ZF system, but some people add the C where the axiom of choice is also thrown in. That's another thing which I would like to discuss sometime. So let's see. Therefore, is CH a theorem in ZFC? In other words, can we prove the continuum hypothesis as a theorem, but or is it a falsehood? I mean, it is. So around what was the time? Around 1940s. I don't know, maybe late 30s, 40s, 1938 to 40, somewhere around that time. This fellow destroyed. When fellow destroyed Hilbert's dream, who showed that CH is consistent. That's all. He said is consistent with the others. That is, he said it doesn't violate any other axioms. It didn't prove it. What he said was, I can append continuum hypothesis as another axiom in the ZF system, and I will have perfectly consistent another axiomatic system. So ZF C plus CH is possible. But at the same time, Gödel also had this incompleteness. What roughly it means is the following. I am not going to, just if any of you want to read these things in a formal way, it's not easy. I wouldn't say it's difficult. I would say it's not easy. Not easy does not mean difficult. Incompleteness, it says roughly, there are statements okay, let me put this inside here, which cannot be decided. Okay, let me put it this. The truth of, falsehood of which cannot be decided. So undecidable. A classic example, I mean, in the classical mathematics was the parallel postulate of the Euclid, that given any line and a point not on the line, there is one and only one line passing to that point and parallel to the given line. That could not be proved using the other axioms. It is consistent with the other axioms. If we drop it also, nothing happens. If we add it also, also nothing happens. It took a long time to do it. So the suspicion was that CH is undecidable. That the continuum hypothesis can neither be proved nor disproved in the axiomatic setup that was available in ZFC. But it was only a suspicion. In order to prove this, you must show that even negation of continuum hypothesis is also consistent with ZFC. And that was done by Cohen in 1963. Sure. That ZFC plus negation of CH is also consistent. So exactly like you can have Euclidean geometry and non-Euclidean geometry. Euclidean geometry is one where the parallel postulate is true. Non-Euclidean geometry is the ones in which the parallel postulates are violated. You can have set theories with continuum hypothesis and set theories with negation of continuum hypothesis. The natural thing would have been at this stage to put continuum hypothesis as an axiom. But somehow or other people are still reluctant to put that as an axiom because it looks so unnatural to suddenly bring one fellow like that. Many of the axioms at least which you can put look natural, but this looks very unnatural to put. So still I don't think any agreement has been reached. People work with the assumption that okay, again if you want to work in set theory without continuum hypothesis, you will have less number of friends than if you are working with continuum hypothesis. But it does not prevent it. Better to have less number of friends and work quietly. So maybe it's worth working with continuum hypothesis negation. And I think these two results by Gödel and Cohen were landmark results in the 60s, in the 20th century on set theory, which in a sense more or less shattered Hilbert's dream that everything can be properly axiomatized. Gödel showed that this, whatever you do, there are going to be problems like this, undecidability problems will be there. Right, but to be honest, I have simply not been. Several attempts are made to really understand the full implications of Gödel and Cohen and their work. I have not succeeded yet. Several decades have spent on that. And nobody has been able to convincingly explain it to me. So I am not going to even attempt doing that because I myself am not sure. But if some of you know it about Gödel's work, and some of the computer scientists are very clever. They seem to understand. So if you have understood that, I would like one or maybe some of you, at least even forget about seem to understood or something. If some of you have exposed yourself to this and read something about this, want to make some presentation on that, it would be nice to have one or two lectures from the audience on this, Gödel and Cohen. In fact, we had a professor in, two professors in computer science in the early 1970s. Professor Nambia, I know that you know him or not, later moved to Jawaharlal Nehru University in Delhi. Professor S.V. Rangaswamy. These two fellows were the people who were very much interested in logic, foundations, axiomatization of this. And I made many attempts to learn from them. What I eventually got was, both of them presented me a book by Cohen. They'd read it. I am still reading it. I don't really understand it. Okay, that's beside the point. So, that's roughly, things about the countability and uncountability I want to say. There is this problem about continuum hypothesis. And the important thing to note is the the plane or the free space, they are all equivalent to the real line, and all of them are equivalent to any small interval. So really small or big is only in the way you look at it. It's not really, big is not that big and small is not that small. That's in a sense philosophical. But at the same time it's really, it's like a 1 inch line is the same as a 10-inch line. All you have to do is put a magnifying glass which magnifies it 10 times and match the one-to-one map. So the only thing is your eye had a better lens, the other fellow's eye had a smaller lens. So his is a small and the other fellow's is a big, that's all. Okay, so I would like to write home this point as we go along to stress the fact the smallness and bigness depends on the context in which you are studying. Okay. Now, in the sense of cardinality, R2 and R, R3 and R, they are same. Okay. But if you look at it from some other point of view, they may be, one may be bigger than one may be smaller. So this point I will try to bring out as we go along. See, what looks smaller in one word is very big in the other word, and what looks big in one word is smaller in the other word. So it is, you have to be very careful that just because one fellow is small in one particular context, it does not mean that he is small in another context. Okay. The next thing I want to look at is, I have at least now, I know these finite cardinals, then I have the infinite cardinal, then I have the 2 to the left not, which is going to be C, then the power set of this power set, which will be now 2 to the C, then 2 to the C, and it will go on. So I have got a hierarchy of, infinite hierarchy of, again, of infinities. You can go on and on and on. Now they also behave like numbers. This is a finite number, these are all now infinite numbers, but they have also been organized as one is smaller than the other, etc. etc. Now we know how to add, we know how to multiply, or even we know how to take powers of these finite numbers. We know what is meant by 3 into 4, we know what is meant by 3 plus 4, we know what is meant by 3 to the power of 4. Now if I want to use that experience to see how I am going to add, multiply or take powers of these numbers, we have to look back at our experience of our numbers, put that result that we know in a language which allows us to see immediately what we should do here. Not as we have seen it. It's not like they take 3 mangoes and 4 mangoes, but how do I do that? What is the set theoretic thing involved in that? You use that idea to define the arithmetic of these cardinal numbers. Okay, so that is the next thing I will quickly do. First I will just make 1 or 2 comments straight away and then come back in the next class and perhaps go through it in little detail. Now suppose I want to add 5 and 6. What do I mean? I write the answer 11. Okay. But this is the abstract version of saying that if I had 5 apples and I also had another bag consisting of 6 apples, together they give me 11 apples. That's the concrete, and in fact most high school mathematics teachers have this habit. At least my mathematics teacher had this habit. If the exercise was, if I had 5 apples in one bag and if I had 6 apples in another bag, if I put all this in a new bag, how many apples will this new bag have? It would be 5 plus 6 and 11. And then you would write 11 donkeys. You have to write 11 apples there. That he insisted, okay? So it's because 5 plus 6 is 11 is a concrete concept, abstract concept. 5 apples plus 6 apples equal to 11 apples is a concrete realization of that thing. So that's what we have to see. What this means is, you have one bag of 5 apples, another bag of 6 apples. They put together give me 11. It's not I have 5 apples and I have 6 apples together, they give 11 apples. It's not that. I have to have one bag separately of 5 apples, another bag separately of 6 apples. Together they give me. That's what this whole idea is. So, suppose A and B are two disjoint finite sets with mod A equal to M, mod B equal to N, then the cardinality of A union B is equal to M plus. Now, this is what I am going to use. This idea I have it in set theory, and therefore I am going to use this to define the solution. If I have two cardinal numbers, I take two distinct representations of, or two disjoint representations of these two cardinal numbers, and take their union and look at the cardinality of their union, and that is defined to be the addition of this. So therefore we have, this is roughly the idea. So if A and B, I have not completely formalized this thing, but just giving the idea, two cardinal numbers such that mod A, and let AB be disjoint sets with cardinality of A to be equal to A, the cardinality of B equal to B, then we define the sum of the two cardinal numbers A and B as the cardinality of A. Now strange things start happening. We will see the strange things will start happening with infinite cardinals. It could happen that A plus A is equal to A, or A plus B is equal to B. Strange things, don't start cancelling things. Okay. So such things can happen. So that's the first definition. Okay. How do you multiply? So now there is a problem. If I have two numbers 3 and 4, the product is 12. But somehow or the other, I have to put this result in a set theoretic language so that I can immediately borrow it for this. So if I have a set with 3 elements and another set with 4 elements, can I construct a set from these two which has 12 elements?
Cross
Product. That's all the story is. Okay. So if A and B are any two cardinal numbers and A, B disjoint, I think in this case even disjoint sets is not enough, such that mod A equal to A, mod B equal to B, then we define A into B to be the cardinality of A cross B. So what you do is, you take a concrete realization of this, a concrete realization of this, do the producting in that concrete realization, that is the Cartesian producting, and then take the back to this abstract version, the cardinality defined by it. So from the abstract to the concrete to the abstract. But that's how you define. We define the product of two cardinal numbers to be this. So here again there will be all kinds of crazy things that will happen. The third one that I want to look at is exponentiation. Why don't I look at divide? Because even in numbers I don't know, m by n will not be a number, isn't it? So there also I don't have that luxury or freedom, so I don't. But I can take 4 to the power of 3, that exponentiation is possible. So therefore, the next question is, how do I define A to the B when A and B are cardinal numbers.
Oh.
I want you to think about it for a day. Now, forget about cardinal numbers. Okay. Let's forget about the whole lecture today. Just a general question. How do you define a to the power b when a and b are real numbers? This has nothing to do with this. Tough? How do you define a to the power of b when a and b are real numbers? You are right, we take it for granted. How do you define 3 to the power of 4? That's no problem. You can write 3 into 3 into 3 into 3, 4.
Except this exponential is also similar to that, e to the power of a, let us say. So in that, like we take the limits like between two, like.
Okay, finally, what's your definition?
Uh,
Yes.
E power b log.
And that's exactly finally what boils down. You have to define it as e power b log a. But then that creates a problem. If a could be negative. So we can define this only if a is positive. Then we can define it as e to the power of b log a. Okay. If you want the answer to be real. So if we have a and b are real, a to the power of b and a is positive, we define a to the power of b as e to the power of b log a. Now before I just concluded, I had a very interesting experience a few years back. I think I told it in the class. Did I or not?
No.
I mean some other class. I thought I told it in this class, in the class, not in this class. Somewhere along the line, I had a mail from some professor from the US, email, asking me, how do you define a to the power b if a and b are n by n matrices? So, my reply to him was, how do you define a to the b if a and b are real numbers? I asked replied him with that question. He said, thank you very much. He understood what is going on. So therefore again, you have to define it as e to the power of b log a. But then the logarithm of a can be defined only for positive definite matrices. And then there are certain questions about what? The commutativity and all. If you take all this into account, finally you have e to the power a to the power of b defined as e to the power of b log a. Oh, incidentally, but that's not going to help you here. That's beside the point. Because it creates more problems. Now I have to define logarithm of a cardinal number and product are defined, but then what is meant by the exponential of a cardinal number? It creates more problems than answering. Okay. So therefore, I want you to look at, just take two numbers, integers, positive integers, and see whether some kind of theoretic thing you can bring between interpretation of m to the power of n. Yeah. So I am going to look at, obviously I will have to look at two sets. One set somehow should represent m, that's size m. The other set should represent with the size with n elements. Okay. I should consider two sets. I don't know which one is coming where. Now from this, I do something, I get the answer m to the n. What do I get? Where do I construct another set which has the size m. Okay, suppose I have said 2 to the power of 3. Either possibly I should try like this or try like this. Okay. Now suppose, I take this, I know the answer is this. Suppose this is the set A and this is the set B. I want to define a function from A to B. Any function, how will you define? This is A, B, C. This is x1. What is, can you tell me one function from this set to that set? Any function.
Everything goes to x.
Therefore, everything goes to x, or everything goes to y, or one fellow goes to x, another fellow. So now, how many functions you can think of?
2 into 2 into 2. 2 to the power of 3.
2 to the power of 3. So, the number of functions from A to B is 2 to the power of 3. Now you have the answer. Suppose you have a card, so this is my A, this is my B. So suppose I have two cardinalities A and B. First I take a set A whose cardinality is what? B. So I will call it B. So mod B is equal to B. And take the set A with cardinality A. And now look at all the functions from the set of all functions from B to A, and look at its cardinality, and that is what I should define as A to B.
Its permutations is repetition, right?
Yes, function doesn't say, I am not talking about one functions. I am simply talking about all functions. Okay, but maybe what to call it, permutations with repetitions. I don't want to use all this. Simply function. This is the only word they have used so far is function. Any function from A, B to A. See, if you want to talk about A to the power B, you must talk about functions from B to A. Take the collection of all functions from B to A. That's a big set. Take the cardinality of that set, and that should be by definition A to the power of B. So A plus B comes from the union. A into B comes from the Cartesian product. A to the power of B comes from the collection of functions. So we can interpret every one of these operations with the integers in terms of set theoretic operations, which immediately gives us the ideas how to define these corresponding operations for cardinal numbers. Okay, I will pick up from here next time, and